All right, let's talk about the unsung hero of our modern world. It's this tiny, tiny component that is literally the reason your phone works, your car runs, and the internet, well, exists. It's called the bipolar junction transistor, and it's about time we gave it some attention. Now, I know that sounds like a huge claim, but honestly, the transistor might be the single most important invention you've never really stopped to think about. It's this microscopic, silent engine humming away inside pretty much everything you own.
And when I say microscopic, I mean it. The very device you're watching this on right now has billions, with a B, of these things inside, all firing in perfect harmony. So, what's their secret? What are they actually doing?
To really get it, you gotta understand the two main jobs that make this little component a true engine of the digital world. Okay, so a transistor really has two main gigs. First, it's a switch, a super fast, super tiny switch that can turn an electrical current on or off. That right there? That's the basis of all digital logic, the ones and zeros that run our computers. And second, it's an amplifier. It can take a teeny tiny signal and boost it into a much, much larger one. And that's actually where the name transistor comes from. It's literally a mashup of transfer and resistor. By moving a current from a low resistance area to a high resistance one, it can amplify a signal, making it way more powerful. It's such a simple concept, but with absolutely world-changing implications. For this explainer, we're going to zero in on one specific, really fundamental type of transistor, the bipolar junction transistor, or just BJT for short. So let's break that name down a bit. First up, bipolar. Okay, so in the world of semiconductors, electricity flows using two kinds of charge carriers. You've got your negative electrons, and you've got these positive holes, which are basically just spots where an electron could be. Bipolar simply means that the BJT uses both of them to get the job done. And junction. This part of the name refers to how it's built inside. A BJT is made of three distinct layers of material, and that creates these two boundaries, or p-n junctions. And trust me, these junctions are where all the real magic happens. So here is the most crucial thing to remember. The BJT is a current-controlled device. The best way to think about it is like a water faucet. A tiny little bit of current on the control pin is like a gentle turn of the handle, but it unleashes a massive flow of current through the main pipe. To see how it pulls this off, we kind of have to pop the hood and look at how it's built. You'll see it's a three-layer, two-junction device with three terminals. And those three terminals have pretty helpful names. You've got the emitter, which, you guessed it, emits the charge carriers. You've got the base, which is that super important control pin, the faucet handle, and then you have the collector, which collects all those carriers on the other end. Now, these three regions are not created equal, and their differences are the whole secret to how this thing works. The emitter is heavily doped, meaning it's packed with impurities to create a huge supply of carriers. The collector is the biggest of the three, so it can dissipate all the heat from collecting that current. But the real star is the base. It's incredibly thin and very lightly doped, and that is absolutely crucial for controlling everything. So how can we stock these semiconductor layers? Well, BJTs come in two main flavors. The best way to picture it is like two different kinds of semiconductor sandwiches. You've got NPN and you've got PNP. Okay, so an NPN transistor has a slice of P-type material, the base, sandwiched between two N-type layers, so electrons are its main carriers. A really handy way to remember its symbol is that the arrow is not pointing in. Now, the PNP is just the opposite. It's got an N-type base between two P-type layers, so it uses those positive holes we talked about. And you guessed it, its arrow points in proudly. These differences decide exactly how you use them in a circuit. Okay, so we've got the structure, we've got the terminals, but how does it actually work? How does that tiny little current at the base control a massive current at the collector? This is the big aha moment. Let's just ask the question straight up. How in the world does this microscopic device get such incredible leverage, turning a tiny little trickle into a raging flood? Well, the secret is putting the transistor into what engineers call the active region. All this means is that we set up the voltages so that the emitter-based junction is turned on, but the collector-based junction is turned off. This basically creates a one-way superhighway for the current, and that's what allows for amplification. So here's how it goes down in an NPN transistor. First, the emitter shoots a massive flood of electrons toward the base.
Now, because that base is so incredibly thin and so lightly doped, only a tiny, tiny fraction of those electrons manage to sneak out as the base current. The vast majority, they've got so much momentum they just blast right through that thin base and get swept up by the powerful collector waiting on the other side.
And this chart just shows it perfectly. That small base current is usually less than 5% of the total. The other 95% or even more becomes that powerful collector current. A tiny input has controlled a huge output. That is amplification.
And it all boils down to this really simple, fundamental relationship. The total current coming out of the emitter is just the sum of the small current that escaped the base and the large current that made it all the way to the collector. Simple as that.
So when you put it all together, you can see why the BJT was such a game changer. It gives you high current gain, it can switch incredibly fast, it's tiny, it's efficient, it's cheap, and it's durable. I mean, what's not to love? It's been the absolute backbone of electronics for decades, for a very good reason. And that kind of brings us to a final thought. We have literally built our entire modern civilization on billions of these little microscopic engines. As we get better and better at making them even smaller, even more numerous, it makes you wonder, what will the world powered by trillions of them even look like?